Hi guys, for the second time of the day, I start out your day and actually that's the group symmetry. Okay, so before we left for lunch, we're very important aspect of particle theory and quantity theory, the concept of symmetry, and we hopefully understood the basics of what it means for a spontaneous symmetry to take place, right? So now we continue on that along with that line and develop the theory of the standard model. And this may involve a very high level technical discussion, but that's not for today. So we try and focus on not the mathematical aspects, okay, but how the big picture and that is related to the physical consequence, right? So I will try to not bore you to death with all epi calculation. Right. Hopefully this works. I will end it. Or yeah. Okay, we're good. Okay. Now, we start with discussion of the big picture things about the Higgs mechanics. So the effect that involves pumping symmetry breaking, which we discussed before lunch. Now, to start off with the Higgs mechanism, consider first a theory with continuous global symmetry. So before we discussed spontaneous symmetry breaking in the context of the discrete symmetry, just the field shift from a pi to a minus started, and that group symmetry A of sign in the mass term, right? Now we're talking about a continuous symmetry, but it's global, right? With a kind of phase shift. The parameter is not dependent on phase time. So then you write down the electron. So this is a electron, and this is a for a symmetry, and we had two serial, right? The pi one and pi two. That's good, and we have some self interaction, right? So this is the mass parameter term, and this is some self interaction. And this is symmetry under the global SO2 group, which means that if pi 1 is basically interchangeable with pi 2 and nothing happens to the electron. So the potential looks like a Mexican, and a Mexican hat in Spanish is called the sombrero. So we call this potential, like here, uh, uh, sombrero potential after the Mexican hat, right? So the potential has denoted is basically a three-dimensional thing. And this whole circle right here, this whole like a well down there, um, or like a ditch inside a curve or something like that. This is all of this is the back. All of this is the minimum. So the minima is kind of lying a plane circle. So this is basically going to be an even number of minutes, right? So the potential is infinite. This one, well, we'll couple of that later. So the minima in Hemke. So minimal line on this thing for now. All right. But that one is like that one is when we talk about the hate skill in general, we'll talk about that uh like that height of that state. But this is not the Higgs field yet. This is just potential. So there actually infinite amount of minima because this is not only 2 points, but rather uh also right. So they lie on this circle, we should like it, on the pi one and pi two thing. And basically that's where you can take each number of minima. Okay. So you can calculate how the minima and whatnot, and you end up with your setting of phi one square plus phi two square gives you this, and you have to choose one by calculating one. You can get plus signs, right? Positive and negative. So you pick one, and once you make that choice, let's say I pick the positive side of the two, and I set the other variable to 0. So I only pick around the phi 1, I pick the positive vector and I want phi 2 is 0. It's my choice. So if I do that, then by changing the So I will redefine my case that I would move from pi 1 here to some pi prime here, because then I know that the minima, this current here, kind of shifts the original to pi 1. And phi 2 set to 0, so that phi 2 prime, if you want to define a new phi prime, is exactly the same as phi 2, because once I make this choice, I'm setting this to pi 2. So here pi 2 is not really changing, right? So I'm shifting my definition of what pi 1 is, what to pi 1 prime. So then you have a new Lagrangian that looks like it. And they're obviously a bit different too. Basically, all you get, you expand the Taylor series across over this minima. And then you ignore the I rubber from pi prime, the Q. So note immediately from the Lagrangian, it's just a basic Taylor expression where you're ignoring the I graph, I over M. From the Lagrangian, you immediately notice something. We really notice there's a mass term for pi 1 prime. There's a kinetic term for pi 2 prime. There's a kinetic term for pi 1 prime, but there is not really a mass term for the pi 2 prime, right? So essentially, pi 2 prime is massless. But remember, he started with pi 2, the original pi 2 field he had a mass term right there. But now, once you have made the choice of which vacuum to city, your new redefined pi 2 has become massless, right? So then, that means that once you have broken the symmetry, so if you were sitting here, either you chose to sit here now, you roll down this thing and sit here now. Once I made that choice, you basically broken the symmetry, and the symmetry breaking has basically eliminated mass flow of the gates that you started with. All right. So this was actually the result that Nambu and Volstone got when they were independently working. One was working in superconductor theory and the other was working in group theory. Sorry, their number. And they figured out the same thing, that whenever a global symmetry spontaneously breaks, you get a massless mode associated with it. So one of the modes become massless, and all those massless modes, Nambu Volstone modes, or Nambu Volstone, or essentially we had Nambu Volstone bosons. So this is Volstone's theorem. This is pretty crucial in defining what really each mechanism, how each mechanism plays a role in defining the standard model. So now this one was just for a real theory. Now you consider a more interesting one. Consider a complex theory with some gauge symmetry. Remember what a gauge symmetry is? You change the gauge field by some parameter, and then the Lagrangian invariant, Abendbeke Lagrangian invariant, you introduce a new kind of derivative. You call it the covariant. And in using that covariant derivative, the Lagrangian needs to be exactly the same as before, but with a new derivative. So this Lagrangian has a symmetry. So this size and side diagrams here are not innerts; they are complex symmetries. That's they're the notations. So you see here, there's a Lagrangian for complex scalar field. So you would have phi prime, a side dagger size, and side dagger size, and side dagger side anywhere. So this is the usual full complex scalar thing, and there you have an interaction, and you have something else attached to it, which is the electromagnetic interaction or electromagnetic Lagrangian. Now, this Lagrangian has gauge symmetry. How do you actually test that? Well, you move to polar coordinates. You move to polar coordinates, and you kind of, to make your calculation easier, you redefine your size to say rho e to the I theta of x. So I theta of x is now just the parameter under which this gauge symmetry is going to play out. And it's a local parameter, of course, because gauge symmetry requires locality, and because it depends on the space time index. And you also have to remember that to protect for this Lagrangian to have a gauge symmetry, not only does the psi need to transform, but also that they need to transform in a nice manner, right? So then that means if you look at this term, and you see if your gauge invariant is protected, you plug in your psi, we define the psi, you plug in your psi here, and you find this term, right? And essentially, if you look at now close to this graph and compare it on both sides, what do you have? You basically have this coupling of AUs and size, and that is now this has an I dash. This is the complex part of this thing. And this the coefficient of I is now this big thing right here. So then your partial use I, IQ, whatever this is, has become this term plus that term. And from there, we can kind of more simple, like we can simplify our notation a little bit more by redefining, by comparing these two AUs, these two terms on each side, and writing AUs and this partial derivative term and redefining it to be another field, simu. These are vector fields. So this is just, a bookkeeping device, making your calculation simpler. First, remove the polar coordinates, and then you do some shift B of your complex scalar fields and your gauge fields, AUs, and you have come to this. You have consistently attention that you're going to simplify the notation by writing this big term as this one vector field. All right. Now you have to find it. You can now write down your Lagrange in front of your polar coordinates and use and whatnot, and you can minimize your so let's say the first derivative with respect to the variable to 0, and then you find what values for rho does your minima here, right? So it turns out that rho is plus minus u square over 2 lambda, and I need to show is that I use the positive minima and I set the theta parameter, the theta 0 parameter after a similar kind of expansion under theta expansion, and I set that to 0 just by making a choice. So I have two variables that I can choose from, rho and theta. I set one to 0. I set the other one to positive. Once I've done that, and again, I want to simplify some more. In my Lagrange term, you will find terms like rho minus rho 0 and whatnot once you're once you are theta extended with respect to this variable, you'll find these kind of terms, and I want to set this to some chi over square root of 2 just to simplify. And after doing all of that, finally, we will arrive at something that's very important. The gauge Lagrange. After doing all of that, you arrive at this deep chunk of thing. You arrive at this Lagrange, and this is known as the gauge Lagrange. So you're applied your gauge theory. You've done all the hard work. You've done the negative. You've done all the predefinitions of the C's and the A's and the whatever, and you have come to this. Right? No, not play. Just natural. That's big M, not an item. So it's just a mass trap or the C field. Okay. All right, but you touched out a good point. Now you just examine the Lagrange. It looks pretty complicated, but let's just break it down. So what are the important terms in the Lagrange? Well, you have the mass curve, and then you have the potential curve. You have the kinetic curve. So kinetic curves are fine, right? You have kinetic curve in the court. Basically, the symmetry lies kind of protecting the mass term or missing the mass term. So here, you see that chi's have a associated mass curve. That's good because this is mass parameter u, and it is squared with the minus sign. It's chi squared, so this is the mass term for chi. And chi is associated. Remember how we find chi? We associate it with the rho field, which rho was the size, the complex scalars, right? So this is actually the mass term for this field. It was the complex scalar size. And this C came up, we redefined the other gauge field, AUs, C, and C squared is nothing but the dot product PU. Okay? And that term has now got associated mass curve. So this term here is important. This is an effect of CU apparently as max from the Lagrange. So this was not the case. AU was just a gauge, did not have a mass curve. So now it has a mass curve. So what happened? Well, what happened was this ADU, these gauge fields, kind of any massless modes that appear when you broke the synapse spontaneously. So remember Bobolson's theorem, you break the synapse spontaneously, some new negative of freedom arrived with their Bolston bosons. Basically, the gas gives kind of the Bolston bosons. Okay, next. So this is spontaneous generation of acid. This is not acid. It's very briefly, that's just the D. It involves a lot more calculation, but I hope you get the big. So you might wonder that maybe we have lost some degrees of weight. So let's see. Before we had two massive scalar particles. Before we had size and side massive scalar particles, and we had also two digits. Right, the AUs were the photon, and the photon had the 2 degrees of freedom. So we have two massive photon particles. There are no back surface associated. But after all of this happened, we actually gave 3 massive vector particles, it seems, and 1 massive scalar particle. Okay, so this is what the degrees of freedom did not really do anything. Basically, it did not change much. We went from 4 to 4, but then in a different kind of particle in the sense that the H beams here, which were masses, became massive and each one the degrees away and became like an extra degree of freedom, the polarization in the longitudinal direction. So this is Peter Higgs and Englert, and they won the Nobel Prize in 2014, I think, after the H discovery in 2012. So they were the first to actually promote this idea, and amazingly, they did it. They did their calculations all independently. The technical mechanism need mechanism, but exactly actually poor product people. So they did their calculations all independent. They arrived at the same result. So the issue was sending multiple people at the same time with the same thing to explain. So, and ultimately they won the Nobel Prize, and then they did all their work back in the 60s, and they got like verified, really vindicated in 2012. So discovery take time. If you don't find something today, doesn't mean they don't exist. You just have to really make a little bit rare things to come. So hopefully we have got the basics of basic pattern. And now let's go for some more complete. How do we actually use AT mechanism when building the Scandinavian particle? So the main idea comes from these two fellows, Yang and Niels. This guy was a grad student. He was a tenured professor, and he was traveling during the summer. And then he just asked him to drop by just to visit during the summer months because Niels didn't get money. He was a poor guest. So he kind of bet me into his university and said, "Okay, I will provide you the summer job, and you just help me out in some research." So he goes into his office and he tells him this idea that he had it. That's where the Yanni theory comes in. All right, that's where he was kind of discovered. So what they were doing is that they knew about quantum later that. They knew about the success of quantum later that. They knew that quantum later dynamics was now the new hero in town, in the sense that quantum theory was finally making sense after Einstein, Springer, and Dyson and others. That's made sense of the activity. But they asked more nuanced. They asked that, okay, QED is symmetric under U1 gauge symmetry, but U1 is a abelian base. It's a very simple kind of group theory. But they asked, okay, is nature more complicated? Can we have, instead of U1 symmetry, can we have non-abelian symmetry that dictates nature in some way, that dictates interactions of particles or field in some way? So they were looking to elevate U1 symmetry to SU2 symmetry in the spread nuclear direction. SU2 is a non-abelian group. So their idea was this. They kind of psi bar and psi, these are fermions, but their fermions were a little bit different. Since they were coupled of nuclear physics, they figured, okay, let's define state with two different fermions. So any one psi inbuilt has two different fermions, F and G. Any different psi bars, we have two different antifermions, F prime and F bar and G bar, right? So they were defining these coupled states of different fermions, which were not kind of the thing at that time. So they wrote down this little button, and basically they tested the gauge theory out front of it. So basically, they asked that they saw that this Lagrangian had this symmetry at this local symmetry, where the tau happened to be nothing but the Pauling matrix field. So basically, they generated some kind of rotation degree of freedom, right? And the gauge field, which is inbuilt in these G's, here written as W. And in these G's, these W's enjoys this gauge period. So under a gauge transformation, W mu transforms like this. W mu changes like this. If W mu changes like this and psi changes like that, the Lagrangian loses its form. So what you have to do, you have to define a covariant derivative, inbuilt in the Lagrangian, and then everything is safe. So they tested the theory out and basically proved that this Lagrangian was invariant under these gauge symmetries of the SC2 local transformations. So this psi's are fermions. They have their psi is state with two fermions, two different fermions. Psi bar is a state two different answers. So, but there was a crucial stumbling block. They went to present this paper, present this research at Princeton, and guess who was at Princeton at that time? It was Foley. And Foley was actually working on a similar kind of thing. And he was working on non-Abelian gauge theories in describing spheres and trying to research spin them up. And he asked, okay, but where are these W mu's? But because these W mu's are masses. So where do you have all these master state bosons floating around? So the only master state boson that we know of is a proton. So where do you have all the master state bosons flying around and we don't even see them? So that was a stumbling block. And in fact, when they published their papers, they kind of said, okay, there are three master state bosons which we couldn't pick. But they still got their paper published because it was an amazing kind of effort. Okay, but it was not complete, definitely. But little did they know that this Yang theory is actually going to be completed by three people: Glashow, Weinberg, and so on. So that's where we go now. And this is here in the Nobel Prize ceremony. This is Abdus Salam, of course. You can recognize this attire. This is Sheldon Guha, and this is the central man right here is one of the great minds of our generation. This is Stephen Weinberg. And basically, it's a very complicated thing, but first you have to realize, okay, now, first you realize that we have talked about QED, we have talked about QCD, right? QED is the interaction of, electrons with light and whatnot. QCD is the interaction of quarks that give rise to sun interaction. But we never really got to a weak force. A weak force is extremely important because the radiations in the sun, the reactions in the sun are kind of mediated by the weak force. The beta decay is mediated by the weak force. But the amazing thing is the weak force is mediated by what we know now, W plus, W minus, and Z. But these W plus, W minus, and Z's don't have an associated, you call it, a weak field associated with it. Remember, in QCD, you had these gluon field mediated interactions. The excitations of the gluon field were gluon. In QED, the excitations of the electromagnetic was the proton, but there's not really any stuff that rates stuff that W just transfers. So there's not really fundamental stuff that we can call W fields and B. So they must be hiding something. And that was their great insight to actually make them come out of it, right? So their insight was that maybe, just maybe, the weak interaction is hiding as inside the electromagnetic interaction. So maybe weak interaction and electromagnetic interactions are not very different, but rather manifestations of the same high energy theory. If you go to higher energy from the observable scale, maybe they're unified. That was their big idea when they formulated this GSW model. So their idea was that SU2 cross U1 was electroweak interaction. So electromagnetism and the weak force merge into this new theory that is SU2L cross U1Y. So U1Y is basically what governs the QED interaction, and SU2L is not govern your theory of fermion interactions when left and right is nature treats left and right different. So that's chirality, but we're not going to go deeper into that. But basically, this is the group that they envisaged that maybe this somehow encodes all of electricity, magnetism, and the weak interaction. So we call it electroweak interaction. So the generators of this group was the weak isospin and the weak hypercurrent. So what is the weak isospin and the weak hypercurrent? Well, they're related to elementary charge and they're related to some motion, some state of the nucleons and whatnot. But these are essentially quantum, okay, that remain that is conserved in weak interaction. So these are the group generators, and from there you can basically generate some algebra and do that and do whatever we did for TVT and QCD, but with a larger group in SU2 plus 1. So essentially, what they ended up with is they did doing all of this similar to QCD and QED. You end up with 3 W1, W2, W3, which had weak isospin, and 1B, which is charged under hypercharge. So these are all quantum numbers. So you get 4 states you do, W1, W2, W3, and the B. So these 3 are charged under weak isospin, and this is charged under hypercharge. But similar to yang anneals, because this is also a non-abelian reactance, right? They are massive. And so this was not a problem for other people to correct. So masses boson coming in, that was a product of symmetry rate. That's fine. But the next step is they implemented is the Higgs gas. So basically what they did was they incorporated spontaneous symmetry rating such that this bigger symmetry rates into U1. So what is the idea behind? The idea behind that is this simple fact that basically at lower energies, if you look at the theory of SUT plus 1, you seem to get 2 different ports. One is the weak quartz and the other is the electromagnetic. The electromagnetic quartz has photons in the The weak quartz may have some other things in the ether. However, at lower energies, they don't really talk about it. Right? But as you go higher, they have this bigger symmetry. So this must spontaneously somehow grade to give you just electromagnetic theory, which is U1. Yeah. Now, how do you carry out SSB or spontaneous symmetry breaking? Well, after spontaneous symmetry breaking of this group into that group, what happens is the W3 and the B, they mix. They kind of mix via what we call a Weinberg angle, a mixing angle. So they form these composite mixture where they can rotate into one another. Okay? And you get 2 things. You get neutral boson. You get 2 neutral bosons actually. Neutral in electrical charge, matter speaking. So you get the Z0 boson, which happens to be massive. And you get gamma, which is the photon, which is of course massive. So you have solved, they have solved the problem of massless bosons lying around. At least they have solved 2. W3s and Bs. B can remain massive because B is going to explain electromagnetism, and photon is lying to any kind of mass because photon is massless. Otherwise, the ability to break. And they have given mass to one of the unidentified photons. So this is the Z0 case. And the other 2 form W plus minus state. Basically, you have a complex field, W plus and W minus. One is the complement of the other. So these are the gate bosons, W plus and minus, and this is also a gate boson. These 3 gate bosons mediate the weak BRAC. So they posited that these weak masses with very high accuracy doing exterior electrolytic reactions, W plus, minus, and 0. So when this was discovered with high level accuracy, they of course had no one to identify as the Nobel Prize winner, but these. So they successfully calculated the masses of these photons. Before that, you see, photon is massive, so the mediator is massive. Gluons are basically, you can see one, but the only lot of water are happens to be U W plus and W minus. The That'll be the very compared to the photon, these are very. So being massive, what does that mean? Well, it means they kind of interact with something, and they interact with what we call the Higgs field. So the Higgs field is some field that protects the atom. But crucially, if you look at any quantum field, so remember the simulation that I showed you, that I showed you at the end of class when I said I'm showing you absolutely nothing. You have this quantum vacuum with many fluctuations, the particle that add particles out kind of going in and out of existence. Well, basically that's the ground state. So for a ground state, it should be the true ground state should be zero. Everything would cancel out. But the Higgs vacuum at this non-zero vacuum expectation. All right. So basically, the Higgs vacuum is not empty. Rather, Higgs vacuum has energy, which is all. Okay. So we call that the vacuum expectation value. And so basically, you can imagine this PU is blanket, and then there is a spike in the blanket, and that blanket spreads all over space-time. So whenever there's a spike in the blanket and other negatives submit, other fields, they kind of interact. Other fields, remember what are these fields? They do any particle with mass. Let's say a quark. A quark field comes in, interacts with the Higgs. Now Higgs has this big thing. When they interact, this big thing contributes some mass to the quark. So that's how they talk to one another. The two fields talk to one another. Now the photon remains massless in the sense that photon is line plane. The HC can do all the talking at once, photon never does. Right? So the HC can be written as 5% pi euro, basically a tablet, we call it, and it's a complex sphere. And it has a radial that looks like this. And crucially, what to notice is the Higgs field is massive. So that means the vacuum is not empty. Higgs vacuum is not empty. It's not zero. So we say the Higgs has a vacuum expectation then. Usually the vacuum expectation that we can expect it to be zero for the ground state, but for Higgs, it's non-zero. It was. So this is what the Higgs potential looks like. Again, some rare. So that crucially, zero, you have the spike. So this is the non-zero vacuum expectation. Okay. Now, finally, we have done all the hard work. Give yourself the pattern of that. We have done a lot in the last 5 lectures, and we are finally arrived at a point to just show you this thing. Nothing much. But all right. So this is the skeleton of elementary particles, and this basically is the best understanding of nature we had so far. Experimentally verified, very high degree of precision. So the human race has done something amazing. This is probably the most, not probably, this is the most successful theory that we have ever of understanding nature at the very fundamental level. So you're looking at radius. So what do we have here? Well, we have groups of things. We have these purple pucks. These are all quarks. Remember, quarks make up protons and neutrons, and they are fundamental constituents of nature. And these are the leptons. The leptons have crucially electron, muon, and taus. Basically, muons and taus are heavier cousins of the electrons. And associated with them, we have also the neutrinos. In the standard model that originally formulated, the neutrinos were expected to be massless. But we now for sure know, and almost surely know, that these have to be massive. All right? So these are quarks and leptons. Basically, this bulb basically makes up all of matter. And we see something very peculiar. You see things coming free call. This is the 3D generation of it. And why? We don't know. And so this is still kind of remedy to explain why things come in free call. Why we have 6 flavors of everything. Those are questions that are waiting for a full answer. And then we have this red column right here. Well, which are the gluons, which is basically the excitation of the gluon field, which mediates strong interaction. This is the photon, which mediates the electromagnetic interaction, basically quantums of light. And these are the W's and G's, which mediate weak area. So these are force carriers, and these are massive force. Okay? So these are big lumbering things. And since they're big lumbering things, they interact with the Higgs media. And then finally, we have the Higgs, which was completed in 2012 with the discovery of the Higgs at around 125 eV. All right. So this is standard one. And essentially what it is a collection of gauge theory. You know that this is related to weak theory, SE2 cross 1. And this is still separate, the strong interaction group, SU3C. But what does C mean? It just means color. So all of SU3 stuff are charged under color. So quartz are charged under color, gluons are charged under color. So when you're charged under color, you experience a strong force. None of the leptons are charged under color, so they don't experience any strong force. Okay? The charged leptons will experience electromagnetic force. However, the neutral one won't. The extremely susceptible and precisely verified is this theory that I said, and it's very good. It has a lot of logic, but sadly, this is incomplete. There's one incompleteness bring up to you at this point. Gravity, good. Yes, gravity is incomplete because we discussed in the first video. When you try to renormalize gravity in quantum field theory, you can't even deal with the HCP at this point. It becomes non-renormalized. Yes, the first thing, of course, there is no gravity, and we know for a fact that gravity is. Otherwise, you can jump from the top, you would fly above. So breaking, of course, we did not experience the standard. So what does that mean? It means that you're not quantum gravity. Everything is quantum, but gravity is refusing to be quantum. So that one, what? Maybe some other. Dark matter, right? So dark matter maybe, but one of the most daring things is part of standard model says. So the standard model has no mechanism to explain the mass of quantum energy derived matter. It has a place for scalar P that is the Higgs, but it doesn't tell me or let me any or any calculation from it that tells me that the mass has to be 125 G. Nothing. Not in the standard model tells me to do that. So the fact that the Higgs is itself part of the standard model is confusing as hell, because the standard model, if you cut off your theory at some high energy, the mass of the Higgs will blow up to that high energy. Maybe not. No. There's no restriction of it. But we have precisely measured the mass of the Higgs to maybe pretty crack on 127 G. But so that is confusing. All right. So standard model doesn't really explain the mass of the Higgs. It allows the Higgs, but doesn't really explain. Similar to how it doesn't explain masses for the neutrinos, but Higgs is more soft in the sense that nothing really forbids neutrinos to have mass in the standard model. Another thing is the renewable gravity that we discussed, some of that no dark matter. We know that our horizon of knowledge is limited in the sense that we only know 5% of the universe, because 5% is nothing. Everything else seems to be dark energy and dark matter. Fast. Don't be certain. State it's 5% of the whole universe. Something else. Yeah. Or, no, there's no it becomes M. Well, maybe the X, but I don't know. Nobody knows. Alright. So also pretty key, there is no explanation for the cosmological constant problem. The cosmological constant happens to be a really small number that is promoting the acceleration, expansion of the cell. So that did not also explain in the standard body part. So we need to go beyond, because why? Well, you have been with me for 5 days now, so it should be evident why you're all here. You want to learn more. And in our thirst for knowledge, we need to go beyond. The first thing that I do is tell you about supersymmetry. So this is the best, easiest theory to look beyond the standard model. And this is a very dear theory to me, because all my research is surrounding the supersymmetries of squatting. So a supersymmetry is a kind of symmetry, but it's super, in the sense that for every standard model particle, you have a super particle. So for every standard model fermion, these are all fermion. These are all speed 1/2. So for every speed 1/2 fermion, you have a integer spinning a boson, right? And there's things divided by one. So if you have a one hat upward spin, you have a zero scalar that we call S up or sub. That's us, right? What's up? So we give these Q delays or the sub, the S turn, the S stop, whatever. And then you have SPGO, Citron, SP1, everything will very easy. Then you have the gauge boson rate dynamo. And these are, field that mediates vector fields that mediate interaction. And personally, the vector fields, you have got for the football, you have the quotidian, which is the fermionic partner. Yeah, for the blue one, there's the gluilo, and so on and so forth. You get there. Yeah. And then for the Higgs, you got the X0. And crucially, it solves a lot of things. Solves a lot of things in the sense that, first of all, but there's a problem. The problem is it doesn't exist. Then why are we working or talking about? Well, it doesn't exist as a perfect symmetry. What does that mean? Well, it means if a perfect symmetry means a electron and electron is same orders everything. So if you can measure the mass of electron and say electron is still 1/2, then there should be no problem for you to measure the mass of electron, which is just still 0. Everything, if you can detect the electron at that same energy, you can also detect the electron. The fact that we haven't discovered it tells me that supersymmetry is not complete, or supersymmetry not really existing in our universe. Then what are talking about? Well, there are mechanisms for it to exist in the sense that it may exist as a broken symmetry. And that's no surprise. Broken symmetries play a critical role in the understanding of that and moment stuff. So broken symmetries are not a problem. So how do we keep supersymmetry relevant? We say, okay, there was supersymmetry after the Big Bang, but then things started to and energies of the universe became smaller and smaller, and now we are here. At some energy, the supersymmetry got broken, and then it's not evident at our observation, but we expect to reach it if we kind of push through our boundaries of energy of observable scales. Right? So it's basically a broken symmetry. And the good part about supersymmetry is, if it's not, even if it's broken, is that it protects everything good about the star. It protects all the things that is good about the star. You cannot really throw away the SAM model just because you're on the opposite. So everything the SAM model explains, supersymmetry models must explain. But then it goes beyond, in the sense that it gives quantum matter candidates. So the quantum matter candidate that immediately stands up is the HE. The HE is a very well-promoted quantum matter candidate. It has all the right characteristics, it's all of the right interaction strengths and all of that to be a dark matter, but it's extremely weakly interacting. It calls the Xeno a WIMP, which is a weakly interacting massive particle. So it's massive, but it's very weak. So the interaction strength is so weak that it's hard to detect. But this is a very well-promoted candidate for quantum. And it explains the Higgs mass. So we see the symmetry between fermions and their superpartners and bosons and their superpartners. But basically, the Higgs mass goes up in the Saturn model because of divergent diagram. You remember what divergent Feynman diagrams were? These dude diagrams, right? It's basically contribute more and more or less and less depending on what theory you're looking at. But some contribute infinities. And those infinities cannot always be thrown away. So the infinities that you don't throw away basically tell me that the Higgs mass can go up to infinity. But in supersymmetry, for every fermionic loop diagram that is infinite, you have a bosonic loop diagram that is infinitesimal of the opposite side. So they cancel out. This nice cancellation actually makes the Higgs mass finite, and would be nice to know that well-promoted models of supersymmetry. Supersymmetry can have many, many models, either results that are model dependent. But very well-promoted models of supersymmetry predicts the mass of the Higgs to be between 150 GeV to 130 GeV. And what we have measured, 125 GeV. It's a very good approximation of the Higgs mass. So that's why supersymmetry seems to be a very nice game. But there is a part at the end of the story. It's not complete. All of that's ill or no, what do you call it? What's that thing? No payoff. But because you try to quantize gravity with supersymmetry, we call that supergravity theories. These are not normalized. Say, okay. And so supersymmetry cannot be complete. So Saddam model cannot be complete. We call it an effective field theory. That is at 1 TeV. Supersymmetry is not complete. It may be valid at a higher energy scale. What is a complete theory? Nobody knows. However, supersymmetry is directly related to the most well promoted theory of everything. That is, when you go to string theory, you have top particle, but then you have strings that are the fundamental consequence of pairs. They can vibrate different modes, give you different particles, and that's those vibrations would have to account for not only standard model but also for supersymmetric product. And essentially, what you have in the end is a superstring theory. And with superstring theories, again, people say it's a problem, and I kind of agree. That's only valid in canyon, but really it's in 4 dimensions. So what do you do with the other hidden dimensions? You say they're so small that you cannot see them or you cannot test them. So these are called compactified models of string theory. So you can compactify n dimensions into small manifolds that do all sorts of weird geometry and topology and mathematics and come up with the standard model and supersymmetry as low energy atomic theories of a mass complete string theory. That is the story of it. All right. Okay. I think this is it. Source. Zero. Yeah, it's basically the field that's arising out of the Higgs mechanics. So it doesn't only encode the W and T, but basically it's W and T are a result of the field. So they're not from starting principles, they're not made up of the WP that not really say. You say, okay, they're made up of the two. No. Those combine accurate by a mixing angle that we call the Weinberg. So basically, they can be rotated as a result of that symmetry breaking. They can be rotating into one into the other. So these are out. When that was met, and from that mixing angle, you measure and calculate the length. So only interaction really that wind show are uh, gravitational, but they're very weak, as you say, but they also exhibit weak interaction. So our goal would be to detect them via weak interaction. So because gravity is so weak, you don't even know what to look. But yeah,
Any Higgs mechanism, it, there was something global issue. Uh, but not maybe it is SU2 or is it?
that's a time wall, right? For that specific theory, it's S. But yeah, the theory is SU2 equal to real fermion level.